everyone, welcome to the Chemistry channel. And today what we're going to be talking about is the bomb calorimeter, or otherwise known as the constant volume calorimeter. So the bomb calorimeter. So to begin, let's talk about the different parts of the bomb calorimeter. So the first part, the most important part of the bomb calorimeter, is the bomb itself. This box, floating inside the water, is the bomb. And the bomb is what carries the reaction, so it contains the reaction. The bomb is also filled with oxygen, and the bomb itself is made out of metal. So the big thing that you have to know here is that the bomb is what contains the reaction. It's also called the reaction chamber. So we have our reactants in here. How do we get our reaction going? Well, in order to get your reaction going, what we do while using a bomb calorimeter is that we ignite a spark inside the chamber to get the reaction going. So what you do is you press the button on the igniter. So this is the ignition, and when you press the button, what happens is an electrical current flows through the wire. The electrical current travels into the bomb, igniting a spark inside, which then causes the reaction to go. So outside the bomb is the water, so this is just water. And of course you have your thermometer. And then the capsule on the outside is called the insulated container. So it's insulated. And this insulated container on the outside is meant to prevent heat flow from outside of the bomb. So this is the different parts of the bomb calorimeter. So how do we get delta H of reaction from this? Well, in reality, we cannot. And the question is why? Well, in order to answer this question, why we cannot get delta H of reaction from this, we have to bring up the first law again. So here is our integrated first law. And remember that we are using a bomb calorimeter, which is constant volume. So since it's constant volume, the work part of this equation is equal to 0. Therefore, delta U is equal to Q. Recall that delta H is equal to Q only when Q is equal to delta U plus P times the change in V. However, this is not the case, so we cannot exactly measure delta H of a reaction using a bomb calorimeter. However, delta U is very close to delta H of the reaction. Therefore, this process is a good approximator of delta H of the reaction. So the same concepts that we used for the coffee cup calorimeter apply to this calorimeter as well. So like the coffee cup calorimeter, we use this equation to figure out what the approximate heat of reaction is. So we use this equation to find out what the heat of reaction is. Now remember that you define the surroundings. However, the surroundings are often all put into one equation. So for example, let's just go on and consider that the reaction itself is the system. So what would be the surroundings? Well, the surroundings would be the O2 in the container, so the O2 in the bomb, the metal that makes up the bomb, as well as the surrounding water outside the bomb. So the Q of the surroundings could be all of these things. Now, all of these variables are often put into this equation. So all of these things are put into this equation. So the heat capacity of the calorimeter, so let's write that down. Heat capacity of the calorimeter incorporates all of these things into it. So therefore you don't have to account for all these individual things. And this is how you would find the approximate delta H of reaction using a bomb calorimeter. So I hope this video helped you understand what the processes of how to use a bomb calorimeter. And in the next video, we're going to be going on to the next method that we can use to find delta H of the reaction. And this method is Hess's law. So that concludes this video, and I hope to see you in the next. See you around.